Hey everybody, this is going to be 3 problems on electric charge and how it relates to number of charges. Number 1, find the number of excess electrons in a negative 1.55 microcoulomb object. So we know that our total charge, Q total, is equal to 1.55 microcoulomb. We also know that the charge on an electron, that's a negative actually, charge on an electron is negative E, which is negative 1.60 times 10 to the minus 19 coulombs. We know the total charge, the total excess charge, is going to be the number of electrons N times the times the charge on an electron. So if we solve for N, we get N equals Q tot over negative E. That is negative 1.55 times 10 to the minus 6 coulombs over negative 1.60 times 10 to the minus 19 coulombs. Plug that into a calculator to get our answer. 1.55 e minus 6 divided by 1.6 e minus 19 to get 9.69 times 10 to the 12 excess electrons. That means 9 times 10 to the 12 more electrons than protons. Next question. A silver spoon has a mass of 55.0 grams. Assuming this spoon is pure silver, find the number of electrons in the spoon. Each mole of silver, 6.02 times 10 to the 23 atoms, has a mass of 107.9 grams. Each atom of silver has 47 electrons. 1. Find the number of atoms of silver in the spoon. 2. Find the number of electrons in the spoon. And 3. Find the net charge of all the electrons in the spoon. So let's start with the number of atoms. We know that our silver spoon has a mass of 55.0 grams. And we want to convert that from grams into, well, we need to find the number of atoms. But we have a conversion factor between grams and atoms. This many atoms is equal to this many grams. So all we need to do is multiply by the correct conversion factor, 55.0 grams, times, well, we need grams on the bottom, we need atoms up top. So that's 107.9 grams is equal to write that a little bit more clearly, 6.02 E23 atoms. Grams cancel and we'll be left with our atoms. So we just plug that into a calculator. 55 times 6.02 times 10 to the 23 divided by 107.9 to get 3.07 times 10 to the 23 atoms. Okay, so there's part A. Part B, find the number of electrons in the spoon. So we know the number of atoms and we want to convert to electrons, and we know that each atom has 47 electrons. We're going to convert it again. 3.07 times 10 to the 23 atoms. We need atoms to cancel, so we know that one atom has 47 electrons. I'm going to just write E minus for electrons. Then atoms cancel. And we're going to be left with our answer. Previous answer times 47. 1.44 times 10 to the 25 electrons. E superscript minus for an electron. Part C is find the charge on all those electrons. Well, we know that total charge is the number of charges times the charge on a single charge, which is just negative E. So Q total is equal to our previous answer, 1.44 times 10 to the 25 electrons times charge on an electron, 1, that is negative 1.60 times 10 to the minus 19 coulombs. Plug that into a calculator. We get 2.3 1 times 10 to the 1, 2, 3, 4, 5 times 10 to the 6 coulombs. That's a ton of electric charge. Now keep in mind, that's not the net charge. That's just the charge from the electrons, but it's canceled out by the charge from the protons. We aren't going to see net charges that large in nature very often. Question 3. Two identical conducting spheres on insulating rods are placed near each other but not in contact with each other. One sphere has a charge of plus 6.6 millicoulombs. The other has a charge of minus 2.2 millicoulombs. A conducting wire is then connected to both spheres so that charge can flow between them. They come to electrostatic equilibrium and the wire is removed. Okay, so before the spheres are connected, do they feel an attractive, repulsive, or no electric force? Find the charge on the spheres after the wire is connected. And then what type of force do the spheres experience after the wire is removed? Attractive, repulsive, or none? Well, before, we have two spheres. We have minus 2.2 millicoulombs and plus 6.6 millicoulombs. So they're opposite charges. They're going to feel an attractive force. Then we need to find the charge on the spheres after the wire is connected. Now keep in mind this is a conducting wire, which means charges can flow freely. Since we have a lot of positive charge in one, a lot of negative charge in the other, those charges are going to try and repel themselves and go and basically even themselves out as much as possible. So we could think about it as positive charge flowing this way or negative charge flowing this way to come to equilibrium. What we do know is that because they're conducting spheres and they're equivalent, they're exactly identical, the charge is going to spread itself out evenly between the two spheres. So for part B, if the charge spreads itself out evenly, then we know that the charge on one sphere, which I'm going to call Q sub 1, is equal to the net charge over 2. The total charge is divided evenly between the two. So let's find our net charge. Well, net charge is just what you get when you add up the charges. Minus 2.2 millicoulombs plus 6.6 millicoulombs. That's our net charge, which is 4.4 millicoulombs. And so our charge on either is going to be half of that, 4.4 millicoulombs over 2, 2.2 millicoulombs, and it is positive because there is an excess of positive charge. Just net charge over 2. Since they're both positive now, plus 2.2 millicoulombs, plus 2.2 millicoulombs, they're like charges, they're going to feel a repulsive force. And if we knew Coulomb's law and the distance between them, we could calculate the magnitude of that repulsive force. That's all. Hope that was helpful. Bye.